Great. Well, with that intro and everything logistically out of the way, I'd like to get us started with some inspiration for discussion today. I've been working on trying to improve building operations for quite some time now, basically my whole career, and in particular using artificial intelligence to do that. So you see the video in the background here. It's supposed to be playing continuously, but let me just get it to go again because it stopped. But it's supposed to be showing you. Well, it's not starting again. Let me just start it. The video is showing you one simple example of sensors that we're using. Is this showing now? No. Let me just share again. Here we go. Yeah. Sensors that we're using to understand how many people there are in a given room. And you may think that, this is very useful information for, say, for example, scheduling heating, ventilation, air conditioning to the room. And indeed it is. But this is information that we can't process manually. You don't want somebody to be counting how many people are coming in. And this is sort of prime example of how we could use AI to do this. But can AI really process this information in a way that we find useful to improve well-being of buildings? That's sort of like the core motivating reason for my talk, to figure out if it's actually true. So in the context of this conversation here and the whole workshop, I think this is the question that is posed, right? And if it can, how AI help us design, construct, operate, and use buildings in ways that promote well-being? And this is a question that we need to answer in different ways. I think the first part is understanding, can it do that? And then if so, how? So I'm going to focus a few slides on understanding what we mean by AI, or at least what I mean by AI, and then give you a few tips for how we should consider these two first questions, the can and the how. And then I'll give you examples for what I think are the possible solutions here. So, working in this space, you may think that AI has already revolutionized the way that we control and operate and buildings for well-being. I just took a quick search on Google News to find like the latest news on these things. These are all from this year, actually from just a few days ago. And the news media may have you thinking that that's the case. But there's also, if you keep digging, a few more details about how autonomous buildings really are, and you will find that a lot of smart home product owners are actually struggling to configure these things. And these are practical issues, maybe not AI issues necessarily, but still very relevant for dismissing or understanding this claim about autonomous buildings being already here. And the story is actually quite old. I mean, we've been working on autonomous buildings and autonomous homes and smart homes for quite some time. I don't know how old you are, but you may remember some of these products that are here from the 80s. And even before then, there are products that are similar. Right, so it's not new. And when we think about AI, I like to think, and this may be sort of a biased view, but I like to think that current AI, largely speaking, is just very good function approximation. So we give some kind of model that we have, data, observations about the world, and we ask it to change its parameters to infer something that we don't directly see in the data. Maybe some latent variable, maybe some parameter of the system, some state. It's basically an inference problem that is supervised. So we have a lot of machinery in sort of the computer science literature and the statistics literature to work with these problems. They're called supervised learning problems. You may be familiar with regression, classification, even reinforcement learning can be thought of as a problem that falls under this category of supervised learning, where there are pairs of observations and labels or variables that you would like to predict. And you just fit the model. In this case, let's say we have function f with parameterized by theta. You change theta so that f behaves according to what you see in the data. That's a supervised case. So I like to think, and this is not my idea, I'm citing here who I saw it from first, but I like this view of how we should think about these functions that we are actually trying to learn, because it gives a lot of insight into what's happening right now with modern machine learning. So you may think of all the possible functions that you can use to create AI to solve these sort of mapping problems from input observations to output. In terms of their complexity. So you can say, I'm going to create a circle where all the functions are there in the center of the circle. They're less complex. As you get to the edge of this, it'll be more and more complex, whatever definition of complex you want. And if you think about it that way, then there are very simple functions that one can use. So for example, I could take one facility manager and ask that facility manager to look at the video footage of these depth sensing. I should have explained what the video was actually capturing. So the video footage was of a depth imaging camera that collects information about how far things are from it, that is located at the top of a doorway, looking down and then looking at basically the heads moving in and out of the space, right? So I could feed that video to a facility manager and say, just count. Your eyes and your brain can actually do that. And this person actually has an F function in their head. It has a lot of bias. It's sort of like it knows how to count heads because it's been trained on countless examples. And it doesn't change no matter how much data you give it. It'll just do the same thing. You can use something a little bit more fancier, and notice that here I'm capturing like a broader portion of the function landscape, because now I have parameters to change, and you can use something, it doesn't matter how familiar you are with the machine learning literature, but there are models that you can use here. SVM is one such model, where you would learn this mapping sort of by showing examples to the model and fitting the parameters of the model until it does that, until it can count the number of heads coming in and out of the space given the input data of the video. And what's been happening in machine learning is that we've been sort of expanding the landscape of functions that we can actually work with, and using a lot more data and a lot more computation to fit those models. So there are very fancy models here, like deep learning models that are can be even parameterized for their architecture. And the more parameters your model has, the more data you, in principle, would require to fit them. Even though there are there are reasons to believe that over-parameterized models like deep nets don't necessarily require a lot of data. They can fit models accordingly. But still, this is the view, the cartoonish view that I'd like for you to keep in mind in the back of your head as you're thinking about AI. Here, in this case, though, the model doesn't make any assumptions about the data, or very little. That's the bias is low. But as you feed it more data, or as you change the data, it will adjust accordingly. It sort of like tunes into the intricacies and the idiosyncrasies of the data, or the errors of the data. So, it's convenient when this function is differentiable, because we have sort of optimization techniques to speed the process of converging into a solution. But the big problem is that this space of possible solutions is actually quite large. We have a domain that is just very complicated, and we can't search it entirely. Even with these constrained models that are sort of deep nets and so on and so forth, they're very flexible, but they require a lot of sort of fine tuning to get to good results. And they may also be brittle, because fine tuning and this large parameter space means that there may be multiple solutions to the same problem. And these solutions may actually work differently when you deploy them in the real world. So that's the sort of backdrop for thinking about AI that I'd like to give. And now let me just bring it back to where I think we could start to fix this problem, quote unquote, in ways that would allow us to actually use AI for well-being in buildings. And the first part is that we have, in addition to having these very powerful models, we have a lot of understanding of how buildings behave, what people want to get out of buildings, what well-being is, what is safe in buildings, what is not safe. And all of these are sort of human values and domain expertise that we can use to reduce the space of parameters that the function approximation needs to search through. And so in some sense, we, the engineers, actually have, and the engineers and the owners and the humans that are actually using the building have a lot of say in how these models behave. And we're not right now using a lot of that in the regular approach to applying AI into buildings. So this is a small note that even when you include all these things, you may still have very computationally difficult problems to solve. So it's not like we should obviate these facts, but it will reduce the space of possible parameters. And a caveat to that is that we actually haven't started talking about additional parameters to those that the function has. So, there are parameters like when you deploy the test for this particular AI algorithm that you have, you use a particular computer under a particular setting, and even the cosmic rays that were hitting your computer at that point may have triggered a small change in the training parameters that you have. And so there are many hyperparameters. I'm giving you an extreme example here, but there are many hyperparameters that we're not explicitly considering. And that's one of the reasons why these problems are inherently underspecified. And when you deploy them in the real world, they may not behave as they were behaving in the test cases that you have. So what can go wrong? A whole lot. So let me start with one thing out of my experience that describes where things can go wrong, even if you're aware of all of these issues. So you remember the video, I'll show it again here. This is, again, good looking from the top, how many people are coming in and out of the room so that we can apportion the HVAC resources sort of efficiently. And we deployed this actually in a number of rooms, more than 50 rooms. And we were thinking that our solution was actually quite useful. We were getting results. The results were encouraging in terms of energy savings, also in terms of thermal comfort. People were feeling fine. But there's a couple of things we forgot to consider here. So first one is, even if the AI algorithm is doing what you told it to do, and even if all the concerns I told you earlier are addressed, you may still have inherent biases that come from not just the data you're collecting, but maybe even from the sensors that are used to collect the data. In this case in particular, the sensor that we were using was a Microsoft Kinect camera that captures depth information, as I said before, using principles of infrared, the way that infrared is scattered and reflected from objects. Infrared actually is absorbed differently by different hair types. And so you can see on the top, the two different people who we were capturing their head using this camera. And then on the bottom, the corresponding depth map for their heads. And the person on the right, so color coding here is like the darker it is, the farther away the object is, and the sort of more red, the closer it is. And so like this head was captured correctly, but this particular head, I mean, the forehead was captured well, but the head itself was not. So we were undercounting significantly just by something that we weren't aware of, right? So you could feed good data to the algorithm, you could actually get some good results, and assuming all of the other caveats that I mentioned earlier are taken care of, you could still have sort of biases that we, as sort of the designers, constructors, operators, and users of buildings, don't want to go in to achieve well-being in our buildings. So that's one example. Another example is maybe overconfidence on extrapolation. So we have done some work on using this same camera that I showed you earlier to figure out if the information coming from these video sources can predict how people will feel in the room when you change the temperature. And so we took a number of people, like 80 participants, into a room. We changed as you can see in the timeline here, we changed the thermostat setting over some time. And we were asking people every 5 minutes, like, how do you feel? How do you feel? How do you feel? And on a scale of, I don't remember, like maybe 5 points, like neutral, hot, but I don't remember the exact details, but it's not relevant right now. We were asking them how they feel. And then we did a mapping between, okay, so these are the temperature changes and this is how people feel. And let's see if we can learn how the parameters or sort of the information that's coming from the video feed can help us predict that. And if you trust what the algorithm is saying, then I want you to not look at the details of this table here, but just look at where I'm pointing at with the red bars here. So these red squares here are showing the classification results, meaning classifying whether somebody is predicted in the right category of how they're feeling according to the model. And the model was trained with different data. First, with just the zone temperature. Second, with the zone temperature, the shoulder circumference, and the height of the person. And then with also skin temperature, clothing, heart rate, and gender. And you may, as you can see from these squares, like the accuracy, and this is in a number from 0 to 1, is increasing as we increase the number of features that are there. And in particular, the big increase is from just using zone temperature to using some information about their body physique. And this may, this may sound reasonable to some people. To me, at the beginning, I was sort of concerned about it. We still published it, and this is a result that we can stand by, given the way that we tested it. But you have to be curious and sort of have an open mind about the fact that this may be an overconfidence in extrapolation. We don't know if this is actually going to work outside of our 80 people sample. But there's a bunch of results out there that are actually of the same category, where small sample size or even large sample size, but not considering many hyperparameters, may lead to bad performance in the real world implementation. So you could ignore all of these warnings and still go ahead and deploy AI in buildings. And even if you solve these problems of human values that I talked about before, you may still fail. And this comes back to this idea that the actual landscape of possible parameters to fit is actually quite large. And the problems in the real world, especially in complex systems like buildings, are very, very complicated. So you can ask, for example, could I use some kind of AI method to learn to control my building and reduce my energy consumption? The answers in the literature that you will get is like, well, you can either use model predictive control, where you specify the model of the building, and then you use that model to figure out what's going to happen in the future as you change your parameters, and then find the optimal set of parameters. Or you can use reinforcement learning, which assumes that an agent can actually learn this by just interacting with the building and then figuring out how to do that. Problem with model predictive control is that it requires for every building a good model, and we have hundreds and thousands of buildings. And with reinforcement learning, the problem seems to be that it just takes a whole lot of time for it to find appropriate solutions. How much time? We did a survey of papers in the last 15 years, and this shows the amount of training time in number of years that it took each of these authors to produce results that were comparable to what they wanted to have, or what they already had in the controllers that existed in the buildings that they were studying. So this is 1 year, that's the line. And so as you can see, it's typically greater than a year of interaction with the building, sometimes as much as 47 years of interaction with the building in simulation. Obviously, you don't want to deploy this in the real world and have 47 years of training before you can actually get a control solution, but that's a whole lot of time. And to switch from just giving you problem after problem to giving you some solutions, we did come up with a way to take this training time down to a couple of weeks back in 2019. And you may ask, how did you do that? Well, integrating domain knowledge and human values does help if we can figure out how. So this one is an example of how we can integrate domain knowledge into these learning machines. The first thing we did is we said this agent that we're training, we called it the new URL agent, because gnus are mammals in the African savanna that once they're born, they're ready to kill. And we wanted our agent to be named after them. But we first pre-trained it on historical data, assuming that the existing controller was doing okay, children learn to do things by looking at other people, well, we could do the same with our agent. And in addition to that, then we let it explore the real world, but we didn't let it explore the real world with a blank slate in its head. We actually included in it a model of how building physics behave. What is building physics? It's a very simple model. This is a linear model, but still it allows the agent to be a lot more sort of efficient in how it collects samples from the environment and optimizes its behavior accordingly. The full details of this are outside of the scope of here, but I would allow you to read if you want. There will be links at the end. Suffice it to say that by doing that, not only did we reduce the training time, but we also achieved significant savings without sacrificing thermal comfort, as measured by sort of discrepancy between the set point and the actual temperature. So that's a winning story. There are additional winning stories that I'm not going to talk about because I just want this talk to be inspiring as opposed to being educational. But my group, and in particular, one of my students in my group has been working on applying these same sort of ideas to not just make learning more efficient in terms of samples, but also to include safety constraints. For example, you don't want the agent to start learning about how to control the HVAC system by all of a sudden heating the room too much or cooling the room too much. So how do you enforce these things in a way that is guaranteed to be the case and not just like trusting this black box? She's done this now also for autonomous racing and other kinds of solutions. So I'll let those things be topics for you to ask me about and not dwell into the details of them. Now, to conclude and to give you time for questions, there's a lot of data out there and a lot of good models that we have to leverage this data and fit parameters and do function approximation. But because these function approximation models are sort of data hungry and not very efficient and somewhat brittle, we need to figure out ways to incorporate both domain knowledge and human values. I talked about safety there. I talked about bias, but there's also privacy, social justice, so on and so forth. And it's not clear how we are going to encode these things. So we need more advances in how we describe these models in ways that are sort of in tune with our definitions of human values and domain knowledge. So that's sort of like the end of here, and I'd like to open up for questions if you have any. I hope I did okay on timing.
Thank you, Mario. We have a couple minutes for questions, and if you posted your questions on the Chi-Storm, Bergen will be moderating for us. And Bergen, can you give Mario a couple questions?
Absolutely. Mario, first of all, thank you so much for that wonderful and inspiring indeed talk. That was a great kickoff talk. So we have a number of questions here. I'm going to pick one, and you talked about the black box approach. So one question here is about how to understand the scalabilities of the AI models. And the follow-up to that is, do we need to retrain a model when there are different people, different seasons, and so on?
Yeah, so scalability is an issue. Both questions are great questions, and they're too wide for me to cover in a few minutes. I was just told that, and I looked at the time. I have a few minutes, but the scalability is a big question for many of these models. You would prefer to have models that can adapt to different conditions on their own, as opposed to sort of the designers needing to re-implement or retrain the model from start. And there's a bunch of literature on sort of transfer learning and other things that I won't bore you with. The second one on the second question was, so like, do we have to retrain for different seasons, yeah, right? So
or different conditions, different people.
Yeah, so depending on what assumptions you make in the model, you may have to, and these two questions are related to each other. In our case, like the physics that we embedded in I don't know if this is where the question was leading to, in which example, but for the new URL, work, the physics that we embedded in it applies to all seasons and applies to all situations. It's very simplistic though, so it's not a very accurate model of the world, but at least it's general enough to cover sort of all the different conditions in which the building could be in. So it depends on what you put in your model.
Thank you, Mario. I know we have only a few minutes to answer these really important and difficult questions. So the next question is related to the bias issue. How do we know what we don't know? And do we need bias engineers who are experts in this area and will be working with us?
Yeah, so that's a great question, also with a lot of philosophical tones to it. So we don't know what we don't know. I mean, by definition, we don't. But we need to be aware that there is this unknown out there. And I think the best way to address this is to not consider the solution as coming at the end, but actually considering the solution as being part of the process. So for example, when I talked about sensor bias or bias caused by the sensor, this is something like you can probably try to patch it at the end, but you actually won't solve it. These systems are already deployed out there. We should have had someone, like maybe a bias engineer, to come into the discussions about designing the system from the start, right? What are the hardware components that we will use? What kind of biases do they incur on? And then learn as we go. Obviously, as these are unknown unknowns, so you don't know the full answer, but that's why the process is what matters and not the sort of point solution.
Thank you, Mario, so much. There are other questions, but we don't have time, but we encourage you to go back to your page and this is supposed to be a dialogue, so you can answer those there. And what you say is kind of a song to our ears. There are several social scientists here actually focusing on the human aspects and looking at these problems from that perspective. Again, thank you so much for the inspiring talk.
My pleasure.